Okay, so welcome back. We'll continue on with our understanding of our graphs and how they apply. So when we've got something that's a bit more complicated, obviously we're just going to treat it like an equation. In fact, some teachers recommend that you write it as an equation so that you can go through and work all of this stuff out. So we'll have an expansion that we'll have to do, and we've got fractions that we'll have to deal with. Okay, so let's do that. 5 on 2 times 3 minus 5 on 2 times x is greater than a sixth minus x. So these are 15 on 2 minus 5x on 2 and 1 on 6 minus x. So let's clear fractions. And what's the one that's going to help us the most? Well, we don't need to multiply. We could do 12, but 6 is just as easy. So everything gets a 6. And if you're wise, you'll just spend the time, first few lines, putting everything through so that you can demonstrate that you understand this process. 3, so 3 15s are 45. 3 5s are 15. 1 minus 6x. Okay. So what we'll do is, what do you think we'll do here? It doesn't really matter. At some point we're going to have the things on the same line. So we'll have maybe add 15x. Add 15x. That will avoid changing the sign around. Add 15x. Maybe subtract 1. So that side will be 45 minus 1, which is 44. That side will be 15x minus 6. 15x minus 6. 15 apples minus 6 apples. So it's 9. 6 and 9 is 15. So it's going to be 9x. So we've managed to manipulate everything with a positive. Now, if you did something like moving the 6 over, that's okay, but when you divide through by minus, you're going to have to change the sign around. Okay, we can change the sign around just for the sake of it. So dividing by 9, so we get 44 on 9 is greater than x. Now, for convenience only, okay, convenience only, we will write this as x is less than 44 on 9. They mean the same. Okay, this is not the rule. Not the rule. Okay, it's just for convenience. So what I'm doing here is I'm putting 44 on 9, and I'm saying off you go to the negative. Okay, 44 on 9. And so what we need to recognise is that that is a more complicated version, but in here, if I had added 6 instead of minusing 15, further down the track I would have had to divide through by minus 9, and that would have changed the sign, and I would have ended up in the same place. So please just be careful of that, okay? In fact, I might just do that. Let's take this step out. Let's take this step out and call it 45 minus 15x, 1 minus 6x. Now let's add 6x. Add 6x to both sides. And at the same time, we can subtract 45. How about we do that? So what that'll give us is 6x. Now it's negative 9x. Haven't changed anything yet. So it's negative 44. Okay, now to isolate the x, what am I going to have to do? Divide by minus 9. Divide by a negative. So we're going to get the cancelling, but we're going to get x is less than. Now the minus over the minus is a plus, 44 on 9. Okay, so coincidentally, we ended up with the same place. All right, as opposed to ending up here and then being convenient. Okay, so the same, not the rule. So just be mindful of that. Sometimes when you choose which way you do your algebraic gymnastics, there are consequences in inequalities that aren't necessarily obvious at the time of doing. Okay, so please just be mindful of that. So that's convolution, not complication. Gymnastics, algebraic gymnastics. So negative infinity, and it's still 44 on 9 with a round bracket. So nothing's changed there. Now, what's the geometric interpretation? I've got to come back to I think it's this line. I think it's 44. I think it's 9x. If I take this line here and think about now, this we do this. This is why I get you to do completing the square on the left-hand side. So in this case here, it's 44 is greater than 9x. So I can, just for the sake of convenience, write 9x is less than 44. So the geometric interpretation would be a very steep value, right up at 44. Okay, let's have a look at that value in the, because we don't want to lose sight of the geometrics. So 9x is less than 44. That's what we got it into a form that we could plot. And so there it is, 9x. So everything that's less than 44. So for our geometric interpretation, it's going to be everything here. Okay, and that point then is 4 9s are 36. So what's that? 4 9s are 36. So 4, 36, and that's 7, isn't it? 36, that's 8 ninths. So 4 and 8 ninths is the point where you decide underneath the y values. So we're treating them like y values, okay? So it's a bit of a different way to look at it, but it's important that you get that. All right, this time when we look at this interval, we can straight away see that this is the result of an intersection, okay? It's an intersection. So the intersection itself requires us to do a little bit of work. Now, to isolate this, we can do this two ways. And the two ways that we can do this are to do what we've been doing in splitting up into intersections. So we can have minus 3 is less than 4x plus 3. And, because that's the intersection model, that's the intersection interval. Intersection interval. We had to recognize that. And that's the one that is the and. Okay? So over here it's 4x plus 3 is less than 11. So we can do the two columns this way. Okay? So we can work it out this way. Now this is not a bad way to do it. Okay? It's not a bad way to do it. But I'm going to show you another way as well, just for the sake of it. Okay? We might want to isolate the x without going through this and business, which would work just as well. Now, it's just as important to recognise that it doesn't matter if I rewrite this for convenience sake, putting the x and everything on that side. I could do that. Okay? So I could just write this as 4x plus 3. Now it's greater than negative 3. So that's the convenience. Okay, that's the convenience. So if I subtract 3 from both sides, 4x will be greater than minus 6, and divide 4 both sides, dividing by a positive. So x is greater than minus 3 on 2. That's that part. This one over here, again, we're in the right direction, so I can just stick with it. So subtracting 3 from both sides, so 4x will be less than 11 minus 3 is 8. Dividing by 2 on both sides, so dividing by 4 on both sides, So they'll cancel. So it'll be x is less than 2. There you go. I was saying it, thinking it and saying it are different. But we want the intersection of this. Okay? So the way that we would do that is that we would draw this as an intersection method. Okay? And when this comes up later, so you know there's a document I posted called the intersection method. So if we put in our negative 1.5 and our positive 2 and just do our intersection. So this one, x is greater than all of that, and x is less than all of that, and this represents the interval. This is the intersection interval. Okay, so look at those two values, and the way that that can be written is we can put this around the other way. Now this is a twist because you can put this around the other way, and you can write it as x negative 3 on 2 is less than convenience again. And look, you can almost put them together. Negative 3 on 2 x 2. So in actual fact, that's the solution interval. Okay, that's the solution interval. So that's a bit tricky, but nevertheless, that's a great one. Okay, now let's see if we can get to that result from up here. We're going to minus 3, but all sides. So you're going to do it everywhere. So you're going to subtract 3 here, and subtract 3 here, and subtract 3 here. So that's minus 6. You'll be left with 4x in the middle, and that'll be 8. Okay? Then we're going to divide by 4. All sides. All sides. Okay? So we're not just going to divide 4 there, we're going to do it there. So you get to choose which way you do it. So that's minus 3 on 2, and that's the final interval, isn't it? That's the same as this one here. Look. See that? So I can take that over and bring it over here. That's our final interval, or the solution interval. Okay? So you can check that. You can put the values in and see if that makes sense. For example, if I check some value, 4, so that's 4's out here, isn't it? 16 plus 3, so that's not part of it. See, that's not part, that makes no sense. But if I do something in the interval like 1, 4 plus 3 is 7, 7 fits in there. So you can check values. You can check values to check the logic. Check values to check logic. You can do that. Okay. So they're a bit of fun doing that. Okay, at some point we could put them into an interval, and let's have a look. Let's see what this one does. So I'm going to do it completely differently. I'm just going to put the interval in. So we're going to have minus 3 is less than 4x plus 3 is less than 11. And I'd like you to tell me what's going on, please. So it's going to do the maths. Oh, look, it's reduced it, and it's showing you the interval. It's showing you the solution interval for this particular set. So that's the geometric interpretation of our interval. Okay, we could get a bit tricky and talk about 4x plus 3. We could plot 4x plus 3. Okay, plot 4x plus 3. And we could say, let's do x between 3 and 11. And let's see what we come up with. 3 to 11. And there's our interval. So our interval is 3. Actually, go a bit earlier. 2. Oops, that won't make sense. Try that. So 2 to 11. So there's our plot. Okay. So in order for the x values to fit, so we need to be a little careful when we're doing analysis to rely on some of the tools that we choose to use. Okay. All right, so I'll leave you to play with the interpretation. We'll just continue on doing some of the mathy stuff now. Okay, so what we want to do here is we're going to make a modification. We're going to change that to a 4. So actually there's a better way to do that. Pop that back again. Just it's on top. So it'll be a bit easier for us to process. Alright, so in this case here, we're looking for the form. Look at the interval. It's got this interval form, so it's an intersection interval. Intersection interval. Intervals are very important in analysis. And so these ideas of inequalities are important because they establish the intervals. So getting used to them can be quite tricky. So if we take the inner pair, 3x is less than x plus 7, and x plus 7 is less than 4x plus 8. So now we're looking at composite functions. So I'll leave you to put Wrk in and see if you can see what the composite function looks like. For the sake of convenience, we could change this, but I'm not going to. So I'm going to subtract x. So 2x is less than 7, dividing by 2, x is less than 7 over 2. That's really straightforward for this one here. Let's see. I could put the number over. That would be okay. So minus 4x, saving myself having to multiply and divide. Minus 3x, and I'll subtract the 7, is less than minus 7 plus 8 is 1. So therefore, now look at this, be careful, divided by minus 3. Negative. So we're going to do what? We're going to change that. Okay. So when we do our number line, 7 on 2 is 2, 4, 6 is 3.5. X is less than 3.5, so off it goes. Negative infinity. And this minus 1/3. X is greater than, so it goes like this. And there's your solution interval. Okay, now it's not obvious that we can put them together. Okay, that we can put them together, but we can. Okay, so we can just if we turn this one around, we would say that x 7 on 2 is greater than x. So that still doesn't fit because we've got the negatives and the positives the wrong way, but that's okay. We're trying things. We're allowed to try things out. What about if I do this one? What about if I change this one around and say, for the sake of convenience, I want the number on this side and less than x. Okay, so if I just put that on that side, I'll get negative 1/3 less than x, and I'll have x is less than 7 on 2, and that lends itself to joining the interval. So minus 1/3 less than x, less than 7 on 2, and that's the interval of interest. Now these intervals are often used in advanced mathematics, okay, to understand problems and to define boundaries and to limit domains and get solutions that make sense because of our interest in making intervals. Alright, so I'll do this one as well, and then that'll give us a chance to think more about uses of intervals. So we'll have a look at this one. So on the left hand side we've got an interval, so we're seeking an interval again. So we've got 3x is less than x plus 7. Intersection with 7 is less than x plus 7 is less than 4 minus 4. So we have now we can subtract the x. That's just adding and subtracting apples. So 3 apples minus an apple is 2 apples. It's less than 7. So dividing by 2, x is less than 7 on 2, which is 2, 4, 6, 3.5. So that's 3.5 or 3.5. Over here, we might subtract 4 apples. Maybe not. Maybe we'll subtract 1 apple. And what you do to one side, you do to the other. So we get 7 and 11 and 3x and divide by 3. So 11 on 3 is less than x. Now 11 on 3 is 3 1/3. So we've got a couple of interesting values that are close. 3 1/3. Okay, but 3 1/3 is slightly bigger than 3.5. Okay, 3 1/3 is slightly bigger than 3.5. So if we plot that, 3.5 and 3 1/3. So let's do that. Let's have a look at that on the calculator. I want to just check that for you so you can see for your own ideas. So 11 divided by 3 as a number is 3.6. 7 divided by 2 as a number is 3.5. So 3.6 is slightly bigger than 3.5. So 11 1/3. It doesn't sound right, does it? 11 1/3. 3 1/3 is bigger than 3.5. So we have to put them this way. So just be careful with that, because that's a real problem, isn't it? Okay, just understanding 3.5, and you can check the numbers just as I did there. Okay, so for this inequality here, it's not included, and it goes to the left. Okay, now we haven't got the x on this side, so just for convenience sake, we can do that. So when we do our interval, it'll be going off this way. Okay, now there's no intersection. There's no intersection, they're not crossing, so it doesn't define an interval, or it's the null set, the empty set. Okay, so this one here would be minus infinity 7 on 2, not included, intersection with 11 on 3, plus infinity, not included, is equal to the set, that's empty. That's how we do it formally, an empty set, or the null set. Sometimes it's referred to as the null set, okay, depending on who your lecturer is. Okay, so those kinds of things are very helpful, and again, I'll let you do Wolfie for the composite idea of functions. Alright, I'll stop this video here, and we're going to come back and use intervals in a different way.